Welcome back. In episode 5, we used the product rule. In episode 6, we used the chain rule, and both times we needed the derivative of sine. We needed to know that the derivative of sine x is cosine x. Both times I asked you to take it on faith and promised the proof would come in episode 7. This is episode 7. Today we pay the debt. Starting from the limit definition of the derivative and the sum of angles identity for sine, we'll derive that the derivative of sine really is cosine, that the derivative of cosine is minus sine, and that the four remaining trigonometric functions, tangent, cotangent, secant, and cosecant, fall straight out of the quotient rule. The whole derivation rests on two limit facts. The first one is sine of x over x tends to 1 as x goes to 0, which we proved in episode 1 with the squeeze-theorem. The second is 1 minus cosine of x over x tends to 0, which we'll prove from the first one with one conjugate trick. After that, 3 worked examples, the full trig derivative table, and a note on why radians, not degrees, are the natural unit for calculus. Let's go. 2 limits will do all the work today. The first one we have already. In episode 1, we proved by the squeeze theorem on the unit circle that the limit of sine x over x as x goes to 0 equals 1. That fact is on the shelf. Take it down and put it in front of you. The second limit is the one we haven't seen yet. The limit of 1 minus cosine x divided by x as x approaches 0 equals 0. Notice that's a slightly surprising statement. The numerator goes to 0 because cosine of 0 is 1. The denominator also goes to 0. So we have a 0 over 0 indeterminate form, just like in the sine case. And yet the answer here is 0, not 1. The cosine version is more delicate. It vanishes faster than x does near 0, while sine x vanishes at exactly the same rate as x. That difference in rates is exactly what makes the derivative of sine equal cosine, and the derivative of cosine equal minus sine, with the signs and the symmetry coming out clean. Here's the conjugate trick. Multiply the numerator and denominator by 1 plus cosine x. That's legal because, for x near 0, 1 plus cosine x is close to 2, definitely non-zero. The numerator becomes 1 minus cosine x times 1 plus cosine x, which is a difference of squares 1 minus cosine squared x. And the Pythagorean identity tells us sine squared plus cosine squared equals 1. So 1 minus cosine squared equals sine squared. The expression becomes sine squared x divided by x times 1 plus cosine x. Now split it. Write it as sine x over x times another sine x over the quantity 1 plus cosine x. 2 factors. As x goes to 0, the first factor is exactly limit 1. It goes to 1. The second factor has sine x on top, which goes to 0, and 1 plus cosine x on the bottom, which goes to 2. So the second factor goes to 0 over 2, which is 0. The product is 1 times 0, which is 0. The second limit is proved. 2 conjugate moves and 1 Pythagorean identity. That's all it takes to get the cosine limit from the sine limit. Everything from here is just arranging these 2 facts. Now apply the limit definition of the derivative to sine x. The derivative of sine x is the limit, as h goes to 0, of sine of x plus h minus sine x all over h. The numerator is the change in sine over the step h. We need to crack open sine of x plus h, and the tool for that is the sum of angles identity, which you saw in trig class. Sine of x plus h equals sine x cosine h plus cosine h sine h. Substitute that into the numerator. You get sine x cosine h plus cosine x sine h minus sine x all divided by h. Now group the 2 terms that share a factor of sine x. The first and the third are sine x cosine h minus sine x, factor out sine x to get sine x times the quantity cosine h minus 1. The remaining term is cosine x sine h. Split the fraction into 2 pieces. Sine x times the quantity cosine h minus 1 divided by h, plus cosine x times sine h over h. 2 terms, 2 limits coming, and both limits are facts we already have on the shelf. Take the limit. Sine x is a constant with respect to h, so it slides outside its limit, same for cosine x. The first limit is the quantity cosine h minus 1 over h. That's just minus 1 times the quantity 1 minus cosine h over h, which by limit 2 goes to minus 1 times 0 equals 0, so the entire first term vanishes. The second limit is sine h over h, which by limit 1 equals 1, so the second term is cosine x times 1, which is just cosine x. The derivative of sine x is 0 plus cosine x, which is cosine x. The promise from episode 5 and episode 6 is finally proved. Notice the elegance. Both terms in the expansion were finite, and exactly one of them survives the limit. The factor multiplying sine x dies completely. The factor multiplying cosine x reduces to 1. The derivative is pure cosine, no scaling constants, no leftover terms, and that clean answer depends entirely on the 2 limits we built. If either one had gone wrong, this formula would not have come out so neatly. Look at the picture. The solid blue curve is sine of x, the dashed orange curve is cosine of x. At x equals 0, sine is climbing through the origin at slope 1, and cosine of 0 is 1. The slope of sine matches the height of cosine. At x equals pi over 2, sine has reached its maximum. The tangent line is horizontal, slope 0, and cosine of pi over 2 is 0. Match. At x equals pi, sine is falling back through 0 at slope minus 1, and cosine of pi is minus 1. Match. At 3 pi over 2, sine is at its minimum, slope 0 again, and cosine of 3 pi over 2 is 0. Match. At 2 pi, we're back where we started, slope 1, cosine equal to 1. The pattern is exact and it holds everywhere in between, not just at the marked points. The derivative of sine is a function that records the slope of sine at every x. And that function, the slope function, is just cosine itself, shifted nowhere. Geometrically, cosine is sine shifted left by pi over 2. So the slope function of sine is sine shifted left by pi over 2. Two curves, same shape, offset by a quarter period. That's the identity we just proved, drawn. For the derivative of cosine, two routes both work and both are short. The first uses the chain rule plus the cofunction identity. Cosine of x equals sine of pi over 2 minus x. That's just a relabeling of the same picture, since cosine and sine are quarter period shifts of each other. Differentiate the right side with the chain rule. Outer derivative, the derivative of sine is cosine, evaluated at the inner, that gets cosine of pi over 2 minus x. The inner derivative is the derivative of pi over 2 minus x, which is minus 1, multiply. Cosine of pi over 2 minus x times minus 1, and cosine of pi over 2 minus x is itself sine x by the same cofunction identity, so the derivative is minus sine x. Done. The second root runs the limit definition again with the cosine sum of angles identity. Cosine of x plus h equals cosine x cosine h minus sine x sine h. Subtract cosine x, divide by h, group the cosine x terms together, and you get cosine x times the quantity cosine h minus 1 over h, minus sine x times sine h over h. As h goes to 0, the first limit is 0 and the second limit is 1. Cosine x times 0 minus sine x times 1 equals minus sine x. Same answer, two different paths. The minus sign comes from the same place either way, from the reversal between cosine and sine as you rotate around the circle. Now the four secondary trig functions: tangent, cotangent, secant, cosecant. Each is built from sine and cosine, so the quotient rule does all four mechanically. Tangent first. Tangent of x is sine over cosine. Quotient rule, the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Derivative of sine is cosine. Derivative of cosine is minus sine. So the numerator is cosine times cosine minus sine times minus sine, which is cosine squared plus sine squared. Pythagorean identity, that's just 1. Divide by cosine squared. The derivative of tangent is 1 over cosine squared, which we write more compactly as secant squared. Secant next. Secant is 1 over cosine, quotient rule. Derivative of 1 is 0, so the first term in the numerator vanishes. The second term is minus 1 times the derivative of cosine, which is minus 1 times minus sine equals sine. Divide by cosine squared. Sine over cosine squared splits as 1 over cosine times sine over cosine, which is secant times tangent. The derivative of secant is secant times tangent. 2 down, 2 to go. Cotangent and cosecant work the same way. Cotangent is cosine over sine. Quotient rule. Numerator, derivative of cosine minus sine minus cosine times the derivative of sine, which is cosine. That's minus sine squared minus cosine squared, which is minus the quantity sine squared plus cosine squared, which is minus 1. Divide by sine squared. The derivative of cotangent is minus 1 over sine squared, which we write as minus cosecant squared. Cosecant. Cosecant is 1 over sine. Quotient rule. Derivative of 1 is 0, so the numerator reduces to minus 1 times cosine. Divide by sine squared. Minus cosine over sine squared, which splits as minus 1 over sine times cosine over sine equals minus cosecant times cotangent. Pattern. The cofunctions, cosine, cotangent, cosecant, all carry the minus sign. The non-co ones, sine tangent, secant, don't. That sign asymmetry is just the minus sign from the derivative of cosine, propagating through the quotient rule into the other two cofunctions, one sign, one source. Here it is, the whole table. Sine, derivative cosine, cosine, derivative minus sine, tangent, derivative secant squared, cotangent, derivative minus cosecant squared, secant, derivative secant times tangent, cosecant, derivative minus cosecant times cotangent. 6 lines. If you remember nothing else, remember the first two. The rest fall out of the quotient rule anytime you need them, in about 10 seconds. But the table is worth memorizing as a unit because you'll reach for it constantly in the next several episodes and throughout integral calculus. The mnemonic that locks it in, the 3 cofunctions, cosine, cotangent, cosecant, all come with a minus sign. Sine, tangent, secant don't. The minus tags along with the co. That's the whole pattern, and it comes from one place, the minus sign on the derivative of cosine, which propagates through the quotient rule into cotangent and cosecant. A practical aside that's also conceptually important. Every derivation we did today leaned on the limit sine x over x tends to 1, and that limit was proved geometrically on the unit circle using the area of the sector 1/2 x with x measured as the radian angle. If you measured the angle in degrees instead, the geometry changes. A sector with a degree angle of x degrees subtends an arc length of pi over 180 times x, not x. So everywhere the old derivation wrote 1/2 x, you'd now write 1/2 pi over 180x. Run the squeeze theorem through and the limit no longer equals 1. It equals pi over 180, about 0.017. And then every single derivative on today's table would carry that factor. The derivative of sine of x in degrees would be pi over 180 times cosine of x in degrees, forever. That's why radians, not degrees, are the natural unit for calculus. Radians are defined so the unit circle arc length equals the angle itself. That definition is what makes sine x over x land exactly on 1, and that landing is what makes every derivative formula clean. If you've ever wondered why mathematicians keep insisting on radians, this is the answer. Every formula from episode 7 onward depends on it. A short note on where today's derivation comes from historically. Newton and Leibniz in the late 1600s both knew the derivatives of sine and cosine, mostly through geometric arguments on the circle that look, to modern eyes, more like physics than analysis. The packaging we use today, sine and cosine as functions of a real variable with derivatives that satisfy clean identities independent of any particular triangle, comes from Leonhard Euler. In his 1748 book Introductio in Analysin Infinitorum, Euler systematized trigonometry around functions rather than around right triangles, fixed radians as the natural unit for exactly the reason we just walked through, and wrote down the identities the derivative of sine equals cosine and the derivative of cosine equals minus sine in essentially the modern form. The rigorous limit-based proof we just gave, with the squeeze theorem stated precisely, is a 19th century cleanup. Cauchy and Weierstrass again, the same mathematicians from episode 1. So the formula is from Euler. The proof we walked through is from Cauchy and Weierstrass. 3 different centuries collaborate on every line. First worked example, the one we couldn't finish in episode 6. Differentiate sine of 3x squared. The outer function is sine, the inner is 3x squared. Chain rule. Outer derivative, with today's result the derivative of sine is cosine, evaluated at the inner, cosine of 3x squared. Multiply by the inner derivative. The derivative of 3x squared is 6x, by the constant multiple and power rules. The product is cosine of 3x squared times 6x. By convention, we write the polynomial factor first, 6x times cosine of 3x squared. Done. Notice, this is exactly the same calculation we did in episode 6 as worked example 2, with x squared instead of 3x squared. The chain rule did the structural work back then. What was missing was a proven derivative of sine. Now we have one. The calculation goes through without a single act of faith. Second worked example. Differentiate tangent x times secant x. Product rule. Derivative of the first times the second plus the first times the derivative of the second. From the table, the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. So the result is secant squared x times secant x plus tangent x times secant x tangent x. Simplify each piece. Secant squared times secant is secant cubed. Tangent times secant tangent is secant times tangent squared. Add the two, secant cubed x plus secant x tangent squared x. Factor out the common secant x. You get secant x times the quantity secant squared x plus tangent squared x. That's the cleanest form. A worked example shows 2 things at once. First, the product rule and the new trig identities compose painlessly. There's no special trick, you just apply the rules. Second, simplification usually finishes the job. The raw quotient rule output rarely is the form you want to write down. Third worked example, differentiate x times cosine x. Product rule, derivative of the first times the second plus the first times the derivative of the second. Derivative of x is 1, so the first piece is 1 times cosine x, which is just cosine x. Derivative of cosine x is minus sine x, so the second piece is x times minus sine x, which is minus x sine x. Add them. The derivative is cosine x minus x sine x. Quick sanity check. At x equals 0, the derivative is cosine of 0 minus 0 times sine 0, which is 1 minus 0, which is 1. Does that match the function? Near 0, cosine x is approximately 1, so x cosine x is approximately x. A function that looks like x near 0 has slope 1 at the origin. Check. The product rule plus today's identities does it in one line, and the answer passes its own sanity check. This is the everyday business of differentiating functions that combine a polynomial with a trig piece. And pieces like x sine x and x cosine x come up constantly in physics and engineering, in damped oscillators, in Fourier analysis, and pretty much any place where you're modeling something that oscillates and decays. 3 quick reasons today's table matters beyond the next problem set. First, physics. The most important differential equation in classical mechanics is the equation of simple harmonic motion, a spring, a pendulum, a tuning fork. The position of an oscillator is a cosine omega t. Differentiate with the chain rule and today's identity for cosine. The velocity is minus a omega sine omega t. Differentiate again, the acceleration is minus a omega squared cosine omega t, which is minus omega squared times the original position. Acceleration proportional to minus position, with the spring constant baked into omega squared. The defining differential equation of every oscillator falls out of 2 applications of today's table. Second, signals. Fourier analysis decomposes any reasonably behaved signal into a sum of sines and cosines. Differentiating a Fourier series term by term is the same operation as today's table, applied infinitely. Third, the simplest non-trivial linear differential equation in the world, y double prime plus y equals 0, is solved by sine x and cosine x, precisely because of today's identities. The derivative of sine is cosine, the derivative of cosine is minus sine, so the second derivative of sine is minus sine. Plug in and 0 comes out. The solution to the whole equation is built from today's 2 derivatives. Every one of these subjects starts here. Where we landed. 2 limits did all the work. Sine x over x tends to 1, the squeeze-theorem fact from episode 1, and 1 minus cosine x over x tends to 0, which we got from the first by multiplying numerator and denominator by the conjugate 1 plus cosine x, and using the Pythagorean identity. With those 2 limits, the limit definition of the derivative plus the sum of angles identity gives the derivative of sine equals cosine in 3 lines. The cofunction identity plus the chain rule, or the limit definition again, gives the derivative of cosine equals minus sine. The quotient rule applied to sine over cosine, cosine over sine, 1 over cosine, and 1 over sine gives the other 4, tangent secant squared, cotangent minus cosecant squared, secant secant tangent, cosecant minus cosecant cotangent. 6 identities, 1 table. All of it rests on radians, not degrees. If we'd used degrees, every formula would carry an ugly factor of pi over 180. 3 worked examples, sine of 3x squared becomes 6x cosine of 3x squared, tangent times secant becomes secant times the quantity secant squared plus tangent squared, and x times cosine x becomes cosine x minus x sine x. Next time, the second great function class, exponentials and logarithms. We'll define e from a limit, prove that e to the x is its own derivative, prove that the derivative of natural log of x is 1 over x, and finally finish the power rule for every real exponent. See you there. Sine and cosine are each other's derivatives, 4 steps around a circle and back to where you started. The way this channel keeps cycling out new episodes is 1 like, 1 comment, 1 share, each one a small rotation forward. Thanks for the turn. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.